Okay, so for this problem, we have the fuel, which is octane, and then the volumetric analysis of the products on a dry basis. So you have carbon dioxide, oxygen, carbon monoxide, and nitrogen. So take note that this is the dry basis, meaning there is no H2O in the analysis, no? So volumetric, to take note of this is the molal basis, meaning this might be used as number of moles in the chemical balance, no? So we want to determine the air-fuel ratio, the theoretical air, and the amount of H2O that is condensed if it is cooled to 20 degrees Celsius, no, at 100 kilopascals. So what should we do here? No, if you want to, let's say, find the air-fuel ratio, we have to do the chemical balance. No, so we have a clue here. We can use the volumetric analysis to solve the air-fuel ratio. No? So we start with the fuel, which is C8H18, plus you have oxygen and nitrogen. So oxygen and nitrogen. Well, actually, guys, this should be 1 plus E times A, but for now, I'll just write here A. This is still the actual, no, or the complete combustion scheme, no, or in some sense, this is actually incomplete combustion, but anyways, this should be 1 plus E times A, no, but I'll just write A here for simplification, no, so that we don't have to write 1 plus E here because we don't really need the excess air. I mean, actually, we need, but we need that for later, no. So let's do this now. You have the CO2, so we can use that as the number of molecules. So 10.02 CO2 plus 5.62 oxygen plus 0.88 carbon monoxide and then nitrogen. So we forgot one, which is the H2O, no? The water vapor, since this is only the dry volumetric analysis, no? So we have YH2O. So we have Y here, A here, and we have forgotten one thing, no? So we are assuming here, if this is the case, we are assuming that we need only one molecule to burn this, no? But the reality here is, since we don't have the actual, no? The inclusion of hydrogen or the inclusion of water vapor here, then we have to assume that this is not one molecule, no, of fuel. If the case is the water vapor is included here in the products, then we can write here 1 actually, no? But since we don't have water vapor in the products, we have to write here N, no? Okay? So to solve for this, you have to solve for each, no? So we do the typical thing wherein we do the balancing of the chons, no? So for carbon, you have X is equal to, 8N. So 8 times N is equal to, so the carbon here, we have 10.02, and then the carbon here. So we only have 1 for each. So 10.02 plus 0.88. So the N here will be 1.3625, no? And then we can solve for hydrogen here. You have N times 18. So you have 18 times N. So the N here is, actually, I'll write this the opposite way. So N here is 1.3625. And then H here is 18. No? And then is equal to, so we only have one component here. You have the two molecules of hydrogen, so 2Y. So therefore Y is equal to, let's solve that one now. So 18 times 1.3625 over 2. Yeah. So 12.2625. So 12.2625. No? Okay. So the last one, we want to determine the A, we can use the oxygen. So for the oxygen, you have two molecules of oxygen. So you have 2A, no? Equals to, so you have two molecules of so 10.02 of oxygen for the carbon dioxide. For the oxygen, you have 5.62. And then for the carbon monoxide, so only 1. And then for the water vapor, so you have plus Y, no, times 1. So basically, this is just 12.2625. Okay? So to find A here, so I'll just solve this on my own. You have, I think I can just divide this by 2, no? So plus 5.62. So dividing everyone by 2, right? So this will just cancel out. And only two components will not have or will have a divided by 2. 12.2625. So A is equal to 22.21, no? So 22.21 for the number of molecules. Now, it is optional to use or to solve for n here. So basically, this is just a way of checking, no, if this is correct. So we have here 3.76 times A. So A here is 22.21. And then let's see if this is equal to 83.48, no? So as you can see, this should be equal to that. So 3.76 times 22.21. So this should be equal to 83.48. It is just off by a bit, but relatively this is the same, no? Okay, I hope this makes sense. So now the next thing we have to do is to determine the air fuel ratio. We can do the molal basis first. So MEA molal, you have the number of molecules of oxygen. So you have 22.21, no? Of oxygen. So you have times 4.76 na lang, no? And then divided by the number of molecules of the fuel. So you have N, no? So you have 1.3625. So typically it is 1, right? But in this case, it is not 1. So you have to divide this by the actual number of molecules. So solving for this, you have 2.91 times 4.76 divided by 1.3625. So you have 77.59, no? Just checking if this is correct. 77.59. Okay. Okay. So 77.59. So it is off in my notes now, but anyways, it is still relatively right. Oh. So we want to find the actual air fuel ratio. So we want to multiply this by the molecular weight of the fuel and the air. So to get the mass, the air fuel ratio, just multiply this 77.59 by the kilomole or the molecular weight of air over the molecular weight of the fuel. So this will be what, no? So the molecular weight of the air is 29. The molecular weight of fuel is 12. Sorry, actually we've solved this one previously. This will be just 12 times 8, or actually 8 times 12 plus 1 times 18. No? So this will be basically 114. So the mass or the actual air fuel ratio can be calculated. So you have 77.59 times 29 over 8 times 12 plus 18. Yeah. So you have 19.74. 19.74. That will be in kilogram of air per kilogram of fuel. Okay. The next one is the percentage of theoretical air used. No. So to find that the percentage of theoretical air used, um, what we can do is we can find the actual, no, the theoretical air needed. So we have to do the balancing again, but we are assuming that this is the theoretical air. So we have to do the CH18 plus well, this is the theoretical, no, just to to make this distinct versus the one that we've solved previously. So A sub T, the theoretical, and then O2 plus you have 3.76 and 2. And then you have the products as you have CO2 plus H2O, sorry, yes, H2O, um, and then plus N2 only, right? So N2 for stoichiometric combustion. So Z, N2. Okay, so this will be, you have carbon, times 2. So you have 8, uh, sorry. So x is equal to 8. And you have here for the hydrogen you have 18, no? So y is equal to 2y. So there, sorry, 18 is equal to 2y. So y is equal to 9. It's basically the same thing, no? And then you have the oxygen. You have a sub t times 2. K is equal to 2x. So 2 times 8. And then plus, sorry, you have only one molecule, so 9. And then to find AT, you have, I think this is 8 plus 4.5. So this will be 12.5, right? So 12.5. Check this. Okay. Yeah, so this will be 12.5, and then we can find the nitrogen as well. But anyways, the nitrogen is unnecessary here. But let's compute it anyway. So we have 12.5. So Z is equal to 12.5 times 3.76, which is about 47. So now to find the actual, the theoretical air fuel ratio, we can solve uh, for it using other different ways, no? But let's just do this the old-fashioned way, no? So you have 12.5 times 4.76. Sorry, this should be molal. Okay, and then over 1, no? So we only have 1 here, so it's 1. So simplifying this, you have an answer here. Actually, we have to solve this. 12.5 times 4.76, 59.5. And then you have here, what do you have here is to find the molecular weights, no? So the molecular weights of the air and the fuel. Okay, the molecular weights of the fuel. So this will be 29. This will be, we will solve this one, didn't we? So this will be just 8 times 12 plus 18, no? So 18, which is, I think, 114. See, no? So 8 times 12 plus 18, 114, yes. So to find the theoretical air, this will be just 59.5 multiplied by 29 over 114. Okay, so 59.5 times 29 over 114. So 15.14, no? 15.14 kilogram of air per kilogram of fuel. So this will be the theoretical amount, no? So to find the percentage theoretical air, so the percentage theoretical air, guys, no, is basically just 1 plus E, no? Okay, so to find 1 plus E, this is just the ratio of the theoretical air, sorry, the actual air over the mass of the theoretical air. So therefore, we just divide this two. So 19.74 over 15.14. Okay. So calculating this, you have 19.74 all over 15.14. And so meron tayong 1.3038, no? So this will be basically in percentage, no? Times 100 pa yan. So 130.4%, no? Around that value. Okay. And then lastly, no? Lastly, we have the amount of water that condenses as the product is cooled to 25 degrees Celsius. So if you can imagine in your air conditioning, let's say your for example lang, no? So for example, you have air, no, that is, let's say, 45 degrees Celsius, or let's say a higher value, let's say 50 degrees Celsius. with let's say 80% relative humidity. So if you cool that down, no, if you sensibly cool this, let's say it becomes 30 degrees Celsius, what happens is it will condense and this will be 100% RH, right? So some of that, no, some of the water vapor in this relative humidity cannot be no, cannot be held by this moist air. So some of it will condense, no? So remember that. So what we want to find out first is what is the dew point temperature of our products, no? Just to figure out if it will actually condense, no, in the first place, and then if it will condense in if it will condense at 25 degrees Celsius, then we want to find how much difference, no, of this how many molecules as it condenses from this dew point temperature up to the slower value of 25 degrees. Because the dew point temperature of this will probably be higher than 25. So let's find the dew point temperature first. So we want to find the partial pressure of water here. No? So the partial pressure of water here is you have on our chemical balance here. So we have Y. So the Y here is 12.26, no? So 12.2625 and then divide this by the total. So the total here is, what is the total? We have to add everything, no? So 10.02 plus 5.62 plus 0.88. What else, no? So you have 83.48, 83.48, and then lastly you have plus 12, the water vapor itself. Okay, so this will be what, no? So this will be multiplied by the pressure, no? So you have 100 kilopascals as given. So this is given. Oh, okay, given. So now we have the partial pressure of the water vapor. We can find the temperature or the dew point temperature. Yeah, we have 12.2625, have 10.02 plus 5.62 plus 0.88 plus 83.48 plus 12.2625. So this will be multiplied times 100. So you have 10.92. No? So 10.92 kilopascals. I solved this before, no? So we can solve the dew point temperature, no, using table 1, and this will be equal to around 47.52 degrees Celsius. Now, as you can see, it is cooled down to 25 degrees Celsius, no? So meaning, because this is 47.52 our dew point temperature, meaning it will reach 100% relative humidity, no? 100% relative humidity at 47.52. So cooling it down, no? Cooling pa, no? After this is cooled even more, it will still be 100% relative humidity. But again, some of it, no, or most of the water will have condensed, no? Okay, will have condensed in the whatever, in the chimney or in the stack. So what should we do here is we can form an equation that relates how much is reduced, no? Okay, so we can imagine that you have this, no? So you have 12.2625. I'll just write here the total. Sorry. No. So the total here is, I'll just write here the total. So the total is 112.2625, no? 112.2625. So this is the partial or the, yes, the ratio of the volume of the water versus the total, no? So we are assuming that this will reduce, no? So at some time it will still obey this ratio, no? Cooling down upon cooling down. So what would happen is from 12.2625. After a while, this will be reduced by the number of molecules of H2O. So we will remove H2O, no? Okay? And then, if this is removed, then also the total number of molecules will also be removed. No? So we have 112.2625 minus the number of H2O that is removed as well. No? So we want to solve here the number of molecules of H2O that can be removed. So this will be NH2O. You can use your numerical methods, or in other words, the calculator to solve for the number of H2O removed. So this should be in what, no? So this is in kilomoles of water. Okay, so you have basically this is just an interpolation, no? As you can see. So 12.2625 divided by 102.2625, and then equals, yeah, 12.2625, and then you have 112.2625, then minus x minus x. So shift solve for x. Sorry, it should be 0. Uh, huh? What? No, 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 no. Sorry, this is not the ratio, no? Oh, sorry. This is not the supposed ratio. I forgot about this. Sorry. The supposed ratio that we should follow pala nga pala is the dew point temperature, or if we assume that, again, sorry. I think I've written this down. I erased pala, no? So at 25 degrees Celsius, sorry, no? So at 25 degrees Celsius, we are assuming that this is also at 100% relative humidity, since going down, no, cooling this sensibly we will inevitably lose moisture. So we want to find the saturation, no, the PSAT, no, of this point. So using your steam table at table 1, we can determine that to be 3.16, no, 169. Ayan, kPa. So, after it reaches 25 nga pala, no? If it reaches 25 degrees Celsius and 100% relative humidity, then therefore, this will be the partial pressure, no? So, 3.169 kPa over the total pressure of 100 kilopascal, sorry. So, this is in kPa of water and kPa of the total, no, of the stack. So, therefore, this should be the ratio pala nga pala, no? Sorry. So, this should be 3.169 divided by 100. Yeah. Okay, so you have 8.99. Yes, 8.99. So you have 8.99 kilomole of H2O, no, removed, no? So we are forgetting something actually here, because if this will be per kilomole of fuel, no, then that will be per 1.3625 kilomoles of this octane. So we have to divide this by 1.36 kilomole of fuel, no? So the number of H2O removed is can be solved, that is equal to answer divided by 1.3625, no? So 6.60, no? So 6.60 kilomole of H2O per kilomole of fuel, no? So that is the amount, no? So if you're saying for the amount, usually it this pertains as well for the volumetric. But if you want to find the mass basis, multiplying this by 1, no? Because the molecular weight of H2O is 1. So basically, this is the same thing as saying this is 1 kilogram of H2O per kilomole of fuel. But you have to convert as well for the kilomoles of, or into kilograms of fuel. So anyways, this is the amount. Amount pertains to the volume, so kilomoles dapat. If you want to convert this, you have to multiply this by the molecular weight, no? molecular weight of the water over the molecular weight of the fuel if you want the mass basis, no? So you have this N of H2O to find the mass basis, no, of the ratio of water and per fuel. Yeah, so that will be all. Thank you guys.